Derivation of differential equations. Let us consider a family of curves represented by the equation y is equals to a times e raised to the power of x. Here a is a parameter or an arbitrary constant. For different values of a, we obtain different members of the family. For example, y equals to 2 times e raised to the power of x, y equals to 3 times e raised to the power of x are two members of the same family, y equals to a e raised to the power of x with a value 2 and 3. To obtain a differential equation for the family of curves, we will need to eliminate the parameter a. To do that, we differentiate y equals a e raised to the power of x with respect to x to get dy over dx is equals to a times e raised to the power of x. Now what we can do, we can replace a e raised to the power of x with y such that we have derivative of y with respect to x is equals to y, and this gives us the required differential equation. By eliminating one arbitrary constant, we obtain a differential equation of the first order. Now let us consider a different family of curve having two parameters given by y equals to a sine of x plus b cosine of x. Let this be equation number 1. We differentiate both sides with respect to x. We have derivative of y with respect to x will be equals to a times cosine of x minus b times sine of x. Equation number 2. Again differentiating equation number 2 with respect to x, we get the second derivative of y with respect to x equals negative a times sine of x minus b times cosine of x. Now we will take the negative common. That will give us negative times y. We have replaced a sine x plus b cosine of x with y as given in equation number 1. Rearranging the terms give us the second derivative of y with respect to x plus y equals to 0. Here we eliminated two arbitrary constants a and b. This gave us a second order differential equation. Similarly, we will find that if we eliminate three arbitrary constants, we will obtain a third order differential equation. Algorithm. Step number 1. We begin by writing the given equation involving the arbitrary constants, the dependent variable, say y, and the independent variable, say x. Then go to step number 2. We will be obtaining from step number 1 the number of arbitrary constants. Suppose there are n arbitrary constants. Step number 3. Differentiate the relation given in step number 1 n number of times with respect to x. Step number 4. With the aid of n equations involving the differential coefficients obtained in step number 3, an equation from step number 1, eliminate the arbitrary constants. The resulting equation is the desired differential equation. Let's try to apply this algorithm by working out few problems. Problem number 1. C times y plus c whole squared equals x cubed, where c is a parameter, represents a family of curves. Form the differential equation. Step number 1. Let's begin by writing the equation. So we have c times y plus c whole squared equals x cubed. Let this be equation number 1. Step number 2. The given family of curves has only one arbitrary constant, c. So we shall get a first order differential equation. Step number 3. Differentiate equation number 1 with respect to x to obtain c multiplied to 2 times y plus c times dy over dx, which is obtained by applying chain rule, equals to 3x squared. Let this be equation number 2. Step number 4, we need to eliminate c. For this, we are going to divide equation number 2 with equation number 1. So we have 2c times y plus c times dy over dx divided by c times y plus c whole squared equals to 3x squared divided by x cubed. The c and c in the numerator and denominator gets factored out, so does y plus c gets factored out. We also factor out x squared from the numerator and denominator of the right hand side. Simplified form of the equation will now be 2 times derivative of y with respect to x all divided by y plus c equals to 3 over x. This gives us y plus c is equals to 2x over 3 times derivative of y with respect to x, or c is equals to 2x over 3 times dy dx minus y. Let this be equation 3 and 4. Now we substitute the value of equation 3 and 4 into equation 1, and this will give us c times y plus c whole squared equals to x cubed. So we have 2x over 3 times derivative of y with respect to x minus y whole multiplied to 2x over 3 times derivative of y with respect to x whole squared equals to x cubed. Performing the algebraic steps, which is left here as an exercise, we finally obtain 8x times derivative of y with respect to x whole cubed minus 12y times derivative of y with respect to x squared equals to 27x. This is going to be the required differential equation. Problem number 2. Y equals to c times x minus c whole squared, where c is a parameter, represents a family of curves. Form the differential equation. We have y equals to c times x minus c whole squared. Let this be equation number 1. As the given equation has only one parameter c, we will differentiate it only once. Derivative of y with respect to x is equals to c times 2 multiplied to x minus c. Let this be equation number 2. The dividing equation number 1 with equation number 2, we get y divided by derivative of y with respect to x equals to c times x minus c whole squared whole divided by 2 times c times x minus c. We factor out the common terms from the right hand side, and that should give us x minus c divided by 2. Rearranging the terms, we get x minus c equals 2y times 1 over the derivative of y with respect to x, or c is equals to x minus 2y divided by derivative of y with respect to x. Now using these two equations and substituting them into the equation y equals to c times x minus c whole squared, we obtain y equals to x minus 2y divided by derivative of y with respect to x whole multiplied to 2y divided by derivative of y with respect to x whole squared. So when we perform the algebra, which is again left as an exercise, we obtain derivative of y with respect to x whole cube equals to 4y multiplied to x times derivative of y with respect to x minus 2y, which is the required differential equation for the family of curves given by y equals to c multiplied to x minus c whole squared. Problem number 3. Y squared equals to m times a squared minus x squared, where m and a are parameters, represents a family of curves. Form the differential equation. We have y squared equals to m times a squared minus x squared. Let this be equation number 1. As we have two arbitrary constants m and a, we shall differentiate equation number 1 2 times. This will give us a second order differential equation. Differentiating 1 with respect to x gives us 2y times derivative of y with respect to x equals to m multiplied to derivative of a square, which is a constant, is 0, minus twice x, and that will give us negative 2mx. Let this be equation number 2, which can be also rewritten as y over x times derivative of y with respect to x equals to negative m. So we're going to differentiate the above equation with respect to x to obtain. So here we have applied the product rule, and that should give us y over x multiplied to second derivative of y with respect to x plus the first derivative of y with respect to x times derivative of y over x, which is x times derivative of y with respect to x minus y whole divided by x squared. And that should give us y over x times second derivative of y with respect to x plus 1 over x squared times dy over dx times x derivative of y with respect to x minus y equals to 0. Multiplying throughout by x squared, we obtain xy times the second derivative of y with respect to x plus x times the first derivative of y with respect to x squared minus y times first derivative of y with respect to x equals to 0. So this is the required differential equation. Problem number 4. Y equals to a times sine bx plus c, where a and c are parameters, represents a family of curves. Form the differential equation. Here we are given the function y equals to a times sine of bx plus c. Here a and c are the parameters, not b. So that means we have two parameters and we will differentiate it twice with respect to x. That gives us the first derivative of y with respect to x is equals to a times cosine of bx plus c. Using the chain rule, we have another factor b multiplied. So that gives us ab cosine of bx plus c. Again, differentiating with respect to x, we have second derivative of y with respect to x is equals to negative ab sine bx plus c. B gets multiplied, which comes as a result of chain rule. So we have negative a b squared times sine bx plus c. We can replace a sine bx plus c with y. So that will give us negative b squared times y. Rewriting the equation, we get second derivative of y with respect to x plus b squared y is equals to 0, and this is the required differential equation.